Hello. Hello.
Yes, ma'am. Yes, ma'am. You are audible.
Okay, sir. Okay. Sir, I think Gaurav sir is trying to speak.
Yeah, hello, Vikram.
Yes, sir. Good morning, sir.
Yeah, good morning, Vikram. Good morning. Sarthak sir is also there, na?
Yes, sir.
Yes, sir.
He is there.
Yeah, good morning, Sarthak sir. I think he is somewhere. So, what is going on, Vikram and Swati?
Good morning, sir.
Yeah, so good morning. Good morning, sir.
Sir, can we wait for another 5 minutes and can start then?
Yeah, sure. Fine.
Yes, sir.
Welcome, Dr. Gaurav.
Yeah, good morning, sir. Good morning, sir. Thank you.
Swati,
Yes, sir.
we can start.
Okay, sir. Okay.
Yeah.
Good morning and welcome you all to the day 6 of FDP on recent trends in frequency selective surfaces for 5G and 6G applications. Today, we have Dr. Gaurav Vashne sir as our eminent speaker. Dr. Gaurav Vashne sir is distinguished faculty in the Department of Electronics and Communication Engineering at NIT Patna. Sir's work has been cited and appreciated globally, reflecting his impactful presence in the academic and research community. Gaurav Vashne sir area of research include millimeter wave and terahertz antennas, absorbers, filters, polarization converters, biomedical sensors, solar cell, graphene-based devices, and reconfigurable devices. Sir, we extend a warm welcome to Dr. Gaurav Vashne, sir, and invite him to take over the session. Please, sir.
Yeah, I think my screen is visible.
Yes, it is visible, sir.
My PPT is visible, na?
Yes.
So thank you, Swati, and thank you, sir, for calling me over here to speak over this topic. Like recently, we had proposed a theory of merging the graphene plasmons to cavity resonance for tunable terahertz functional devices, and few PhD students have been awarded their PhD degree on the basis of this theory, and we are conducting further research in this domain to develop tunable terahertz functional devices which can be suitable for 6G applications.
Gaurav
So
sir, sorry
yes,
to
sir.
interrupt.
Yeah.
Kindly make the presentation in full screen mode.
Okay. And now I think this is fine, sir.
Yeah, it's fine now. Yes.
Uh, so this topic hopefully will be useful for the people who are trying to work in this domain of terahertz functional devices or 6G devices. Uh, so before we start about this further topic, we have to think over it. Means what is that universe? So we are having universe. This is composed of two things. One is called wave, and another one is matter. One is wave, another one is matter. So wave, there can be two categories of wave. One is the longitudinal wave, another one is the transverse wave. Everyone knows this basics from the 12th standard and before that 6th standard too. Like sound wave is a mechanical wave that is being called as a longitudinal wave, and these are being defined, being categorized on the basis of their vibrations along the direction of propagation or transverse to the direction of propagation. The second one is the electromagnetic wave. This is a category transverse wave. Once any type of wave, either longitudinal or transverse, interact with the matter, there is a resultant phenomena that is called resonance. So ultimately, this is the only thing that we require. Any design means electromagnetic researcher require this is called resonance. So here, if we are the antenna designer, antenna researcher, or any device researcher which can work on the basis of electromagnetic resonance or any other kind of resonance, so we can think about this dipolar arrangement. So if we are thinking about this dipolar arrangement, like everyone knows about it, like every this charge with equal and opposite polarity separated by a particular distance can create some dipole moment, and this will be called as dipole. Once this dipole arrangement of any charge, equal and opposite charge, is oscillatory in nature, you can understand this is the oscillatory dipole. So it will start providing radiations into the free space. And this concept has been exploited in designing this dipole antenna. The simple concept of a dipole antenna. There are four categories of dipole that we had studied in your UG antenna engineering. First one is the infinitesimal dipole having length around lambda by 50. Second one, short dipole having length around lambda by 10. Third one is finite length dipole, can have length of the order of lambda, and then half wave dipole, exactly the length equivalent to lambda by 2. So here we would like to discuss about this lambda by 2, the resonant dipole. This, you can see the charge distribution over here on the arms of this dipole arrangement of this antenna, maybe metallic wire. So you can understand this is a kind of oscillatory charge, and it can provide us some radiations into the free space. So there is a lot of physics that you can understand in your own way. What is happening behind this, means there are multiple books available at the UG level that you can prefer to understand the basic physics about this oscillations of the dipole and how this is providing radiations into the free space. Furthermore, our concern remains like how to design this resonator, this resonance lambda by 2 resonator. One thing that we can understand, like lambda by 2 resonator, if this is working as a resonator for a particular frequency, then it can provide us some oscillatory dipole that can behave as an antenna. In a similar way, like if we discuss about this longitudinal wave resonance, that you can understand there are multiple ways to obtain the resonance from the interaction of matter and longitudinal wave. So here the dimension of this EM dipole, specifically if we are talking about this lambda by 2 resonator, so that resonant frequency that we can calculate, this is in that way, okay. And furthermore, that we can understand, like this is the basic means cavity model, waveguide model, that you can understand this, like resonant frequency is reciprocal to the dimension of any cavity or resonator. So if dimension is resonant frequency we need, if resonance we need in gigahertz frequency range, then dimension of resonator becomes in millimeter range, and this has been scaled down if we just want to get the resonance in terahertz frequency range. So resonator size will be of the order of micrometer. That can be understood from the different basic electromagnetic mathematics related to electromagnetics that we can understand, and this basic mathematics we are going to utilize to design anything that we are going to discuss in further course of this lecture. Here, if we discuss about terahertz frequency, so everyone knows, most probably the people who are working, and right now engineers, researchers who are going to grab something in this frequency range of electromagnetic ranges, and this range from 0.1 to 10 terahertz will be called as terahertz frequency range. This is lying beyond microwave frequency range and just before this far infrared frequency region. So there are multiple advantages of working with terahertz frequency range that one can understand from the multiple sources. And then in terahertz we can come towards this higher frequency range that comes towards this optical frequency range. That is not our concern in today's lecture. This is our concern to work with just 0.1 to 10 terahertz. Okay, so here this is frequency gap. That one thing that we can understand, like this frequency range, if this is lying way beyond this, between this microwave and infrared, then it can exhibit the properties of infrared frequency ranges as well as microwave frequency range. Up to certain terahertz, means 3 terahertz maybe, and beyond that it can provide us the radiations in form of electromagnetic wave like microwave, and beyond that frequency up to the higher towards this far infrared frequency range, we can have some radiations like a straight line, like a laser, that we can think over it. So this is the beauty of this terahertz frequency range, can provide us the characteristics of microwave and this infrared both, and we can utilize this in multiple applications. Furthermore, there is one more thing that we can understand, like terahertz wave does not penetrate, means it can penetrate to the towards this matter, biological tissues, but it does not deform this basic unit cell structure of any biological tissues. So it is expected like there is no harmful effect of terahertz wave like X-ray and other wave electromagnetic wave frequencies signal that we can understand. So these natures of terahertz signals, just because of these properties, this can provide their applications, its application in pharmaceutical industries, and so many things are there. Sensing, communication, the most prominent thing that we are expecting in the future upcoming days. This is 6G communication system in lower terahertz frequency range that can be, it is expected like this, a 0.1 to 3 terahertz frequency range will be exploited in 6G terahertz frequency somewhere. Multiple channels will be provided in that frequency range. And here, like there is most important advantage that we can understand, like this bandwidth, this being offered by this terahertz spectrum. Okay, like one thing that we had studied earlier, like any resonator having fixed resonance spectra. Okay, like if we draw some reflection coefficient or it's a resonance curve in terms of reflection coefficient, then we can understand this is the reflection plot. If this frequency is in gigahertz range, microwave frequency in gigahertz, and whether this is in gigahertz or in terahertz, this resonance spectra remains constant. Only thing is that, like if we are shifting from gigahertz to terahertz, this resonance spectra has covered, the bandwidth has been scaled up by 10 raised to the power 3 while shifting from gigahertz to terahertz. Resonance spectra is having its a fixed nature. Any cavity, any resonator can provide the fixed, this resonant spectra of fixed nature. Only thing, like if we are scaling up the frequency, means we are scaling down the dimensions. Only thing that we can attain wider bandwidth. So that's what we are attaining over here in the terahertz frequency range in comparison to this microwave frequency ranges or any other lower frequency ranges. We can attain the broader bandwidth, and using that channel capacity theorem and other bandwidth data rate relationship that we can understand, like broader the bandwidth of any channel can enable the broader data transfer rate. So these were advantages of terahertz frequency ranges. Our focus is to discuss about these terahertz devices. Like we are having right now, researchers are working on multiple devices that we can discuss here. We'll consider two devices mainly: antennas and absorbers. Most of the research, mean multiple research groups are working in these two devices, which can enable multiple applications. Like these are prominent devices. Antenna, that we can understand, like this is a key element for any wireless communication system. Any wireless system cannot be imagined without this antenna element. This is anthem element of any communication system, which is being expected wirelessly or handheld devices. Second one, absorber. This is becoming popular nowadays just because of its a multiple utilities in multiple domains, in medical, in daily life, in other, that we can understand, in security, defense, and stealth applications, and many more that we can imagine. Sensing as well, that we are going to discuss. Antenna, everyone understand, like this is a kind of transducer that converts the wave from electrical to electromagnetic and vice versa, depending upon this is being utilized at the transmitter and receiver. And absorber, what is that absorber that we can understand using that example of this curtain. So here at optical frequency we place certain some curtains on our window. So what is that phenomena? There are three things which are related to physics: absorption plus reflection plus transmission. This is complete wave. So any wave can be split in three parts. It can either be absorbed by particular matter, or can be reflected by particular matter or can be further transmitted into another medium. And this is a complete wave that we can understand using some basic physics. And if we are deploying here, if we are deploying this curtain at the windows, so what is happening that you can understand the basic physics, like what is happening, some electromagnetic signal is falling on this curtain through this window, and then most of the part is being absorbed. Little amount will be reflected and very insignificant amount will be transmitted depending upon few things. So what are those few things? Like absorption will be directly proportional to concentration of threads being utilized in this curtain, C, defining the concentration. And this second term is it's a thickness, T. How much is the thickness of this cloth? So here absorption is directly proportional to the concentration of matter and thickness over which this wave is traveling. So here we can understand is if we just want to remove this proportionality constant, and there will be some parameter that will be called as extinction coefficient, and you can study about this extinction coefficient more detail. This is called Beer-Lambert's law that can define the absorption by means absorption of any electromagnetic wave in any material. So here this phenomena is happening at optical frequency, means optical frequency specifically in visible frequency range from 250 to 750 nanometer range, and a little bit beyond that as well, nanometer range. So here we can understand what is this cloth. We can imagine about it's a microscopic view. There are multiple threads which are vertically arranged and horizontally arranged. So we can think over it like one thread. There is one unit cell structure, square shaped resonator, and this square shaped resonator is spread over the whole dimensions of this total window in area over which this cloth is covered. So one thing that we can understand, this one unit cell is repetitive in nature. Another very important thing that we can understand, like response of one unit cell is independent from another unit cell. There is no coupling between two unit cells. Means what is the usage of this second point? Means if we just try to imagine, if we means cut this cloth over a small length, or if we reduce the size of this window, then definitely we can cut the cloth and we can reduce the number of unit cells of this being formed by the combination of threads, and ultimately there will be the similar absorption over this frequency range, this wavelength range, 250 to 750 range, 750 nanometer. So ultimately we can understand this physics like reduction or increment in number of unit cell in this curtain does not means it's not being impacted by its number or its arrangement. Only thing that is required, it must be arranged periodically, that we can understand. In fact, we can turn it, we can do anything with this, and rest of the things you can imagine whatever we can do with this curtain. So this is a basic example of curtain, basic example of absorber that we are utilizing at optical frequency in visible frequency range. In the similar way, we can design absorbers for other frequency ranges. By utilizing this concept, we can design absorber for terahertz frequency ranges, for microwave frequency ranges, and so many frequency ranges we can design absorbers. You can understand. Only thing that two points that we have to understand: the periodic arrangement is required to spread over the dimensions. Second one, there should not be coupling between two unit cells consecutively. Okay, that is also just a point to understand. Our concern of discussion remains the devices, terahertz functional devices, and this theory that we had proposed right now, theory of merging the graphene plasmon resonance to the cavity resonance. So what is that theory? This theory is applicable at terahertz frequencies and beyond that, maybe at optical frequencies too. but this will be specifically calculated here. We had proposed this for this point from 0.1 to 10 terahertz frequency range, because there are multiple properties of different materials which are existing and which can be employed to work out with that theory that we are going to discuss over here. So here first we have to understand what is that resonator. We had understood that lambda by 2 resonator, the concept of resonator. The similar resonator concept we are going to utilize in designing the multiple devices. Like people who are working on antennas, they can work on different devices because they know the concept of resonator. So similar thing that we can devise over here, like this is microstrip patch antenna, and this is the resonator, this is feed line, and this is port. There are some other parts, substrate and ground plane. Okay, so this is resonator. So dimension may be of the order of lambda by 2, specifically if this is working at the fundamental, working with the fundamental mode of operation. Its operation is dependent on the fundamental. Second case is this dielectric resonator antenna. Here this resonator is made up of dielectric material, and you can think over it like if this is of dielectric material and other parts are means coaxial feed line or any kind of feed line. Okay, and then there are ports and other parts, substrate, ground plane. This resonator, if this is specifically working with fundamental mode, then its a dimension may be of the order of lambda by 2 or finite, any finite length dipole. Okay, so this is microstrip patch, and here this is resonator, this is dielectric resonator antenna, and this is here this resonator. Third one is this absorber, maybe filter, maybe modulator, maybe other frequency selective element, or maybe metamaterial structure, unit cell structure, or reflector, or any other thing that you can imagine, maybe solar cell too. So it may contain three parts. Basically this is reflector, maybe ground plane, that somebody can understand in that way. Second one is the dielectric spacer or substrate, and third one is the resonator at the top. So it's a dimension if this is working with the field distribution or dipolar field distribution equivalent to this plus minus q, and maybe this is of the order of lambda by 2 or any other finite length dipole that you can understand. Finite length, the meaning of finite length that you can understand means multiple times or fraction of wavelength lambda. One thing that we can understand, any device whichever working with certain resonators can utilize resonator or dipolar arrangement or dipole resonator of multiple dimensions. Here we are focusing on approximately the resonator is having the dimension of the order of finite length dipole or lambda by 2 exactly, maybe. Okay, this is a generalized concept that we can understand. Only we have to keep one thing in mind, like whether this device is working with the fundamental mode or any other higher order mode. So here we are considering that device is most probably working with the fundamental mode or nearby resonant mode, that we can understand. And here next one is this filter or MIMO antenna. Okay, so all filter is another device, and this is also exploiting a resonator and can have multiple ports, port 1, port 2. Okay, and if this is a filter, then there will be high quality factor, means nothing will be radiated into the free space. And if this is an antenna, means everything will be radiated into the free space. Everything stands for whatever you are applying power at port 1, it will be radiated into the free space, and nothing will be received at port 2. And if you are designing a filter, means once anything radiates into the free space, everything, then its quality factor will be smallest, lowest. and once this is a filter, means nothing will be radiated, everything will be confined within this resonator and will be propagated to another port by using some frequency selectivity, then this will be called as filter. In that case, this can provide high quality factor that we can understand. So here we can further categorize. First we will try to discuss about terahertz antennas. There are three categories of terahertz antennas. We had prepared this over here. First one is metallic or dielectric resonator. Okay, second one graphene antennas. The third one hybrid antennas. So based on the material being exploited in a resonator, being utilized in the resonator, uh, we are defining these category. Like first one, if this is a metallic resonator, this is metallic antenna. Dielectric resonator, dielectric antenna. Graphene resonator, graphene antenna, or hybrid kind of that. This is our concern to study about this hybrid antennas. On the for this category, we had proposed our theory of merging the graphene plasmon resonance to this cavity resonance. Mostly in case of metallic antennas, this resonator is of metal, or in case of dielectric resonator antennas, resonator is of dielectric material. Okay, here this is antenna symbolically just presented, but this is a metallic antenna with dielectric loading. Dielectric resonator antennas is having its resonance from dielectric element only. That's it, without any metal. So this is just a symbolic presentation. You can understand. Means any antenna which can contain dielectric resonator that we had discussed earlier. Here, one thing that we can understand in the case of terahertz antenna, whatever we are working, it's a dimension of antenna. This is an antenna array. One research group has proposed and fabricated this antenna array, and this is size that you can compare. This is head of matchstick, less than head of matchstick. Okay, and second, this antenna is working within this frequency range. This is around sub 1 terahertz or beyond that for broadband applications. Second one, this is dielectric resonator antenna. Okay, and here there's some structure you can go in depth. This has also been fabricated, okay, by this research group, and this was working in sub 1 terahertz frequency range, around 100 gigahertz and beyond that. Results have been measured. So there is a challenge, like in case of metallic and dielectric resonator based antennas and other devices, means one thing that we had understood, these devices having dimensions of the order of that micrometer, and this is much lesser than head of matchstick. So every time we cannot fabricate these devices. Likewise, the devices we are fabricating at microwave antennas, microwave frequency ranges. And simply we can apply some manual efforts to fabricate those devices which are working at the microwave frequency ranges. We can take scissor, we can cut the different material, we can paste the copper strips, and we can just measure the results, and we can employ those devices somewhere in applications. In micrometer dimensions, we cannot do that manual efforts. We cannot go for that. Means also one thing is required, like if micrometer dimension is changed a little bit, there is a little bit change during fabrication, then the response of the device will be, as you can understand, it will be highly intolerable. This may be. So in that case, this design fabrication, each time fabrication of this micrometer device is very cumbersome task. We need high-end machinery. So one thing is required in those devices. This is called tunability or reconfigurability. Okay, so what is that tunability or reconfigurability? Like here we can take some example. This is for UG students, means who are going to start their career in this in developing the tunable devices. What is tunability? What is the meaning of tunability? That we can understand. Like we are having a fan. Generalized. This is just a generalized example, and this is regulator. Suppose this regulator has not been invented right now. So what will happen? We are having only fan. So you can imagine, like we cannot change the speed of this fan. This rotation RPM cannot be changed. and if there are multiple users in particular room, they may require multiple speeds of this fan. So this is a problem. In fact, this is also time dependent. In multiple times we can require the multiple speeds of the fan. Only if we are not having this regulator, we cannot change the speed. So this is the problem. So this is a tiny element. This is externally working to this device. This is employed externally to this device and simply regulating its speed, its outcome. So this is called electronic or electrical reconfigurability in the speed of this fan. In the similar way, we can utilize this concept in designing the micro scale devices. Okay. So in case of micro scale devices like antennas, absorbers, and other things, we can develop such things which can tune the response of the device externally. Okay. And why we just need to tune the device? Like one point is like we cannot fabricate this micro scale devices every time. We have to we have to develop reconfigurable concept of reconfigurability just to avoid the refabrication. And point is like if we fabricate device one time, then we can just, if we just need another response, we just tune it using some external element. You can understand. This is the one example that we can understand. Here band notch is being means generated in some ultra wideband response of some device, maybe antenna. So here there is one parameter for this particular value. This band notch frequency is being changed over frequency. So you can understand we can filter out this number of frequency bands as per our requirement. Whatever frequency or whatever channel we just want to filter out from the response of particular system, we can just externally tune it using some regulator kind of device. So here in the recent days, graphene is becoming popular for this purpose. What is the advantage of graphene? Is graphene can provide us some electronically reconfigurable Fermi energy. Like we can understand, this is having this is conduction band in any material, and this is valency band in any material, and this is Fermi, this band gap energy. This band gap can be tuned in general semiconductors. This band gap can be tuned by using doping, external doping. But problem is that in case of doping, this doping can be done at the time of fabrication only. Once you had fabricated any device using semiconductors, you cannot you cannot tune its response like fan and regulator. Okay, so this is a problem. So graphene can facilitates us with that feature. This is having some direct conical band gap structure, and the band gap can be, it's a conical tip points can be separated and overlapped with the help of some few techniques, and these are three techniques. First one, chemical doping. You can understand likewise in semiconductors, but this can be done at the time of fabrication only. Second one, external DC biasing. Yes, this is most prominent and fabulous technique that we are going to utilize, and researchers around the globe are working with this technique. They are exploiting this technique to work with that to attain the tunability, electronic reconfigurability. Like means we can take some variable voltage supply, okay, DC voltage supply, and variable DC voltage supply, we can just tune this DC voltage and its a Fermi energy will be tuned. You can understand, and once you are able to tune the Fermi energy, you will be able to tune its, means if you are able to change the band gap energy, you will be able to change the conductivity. In the similar way, graphene, you are able, if you are able to tune its a means very DC voltage applied on the graphene, you will be able to tune its a band gap and Fermi energy level. So this is the important thing that we can understand. And what is that graphene? One more thing, third category is that like application of magnetic field. This technique is also applicable to tune its a Fermi energy, but generation of magnetic field is is little cumbersome task that you can understand. Okay, so this is most flexible technique that we can utilize in graphene to tune its Fermi energy. What is graphene? For just most of the people, I hope means know about that graphene. That this is a simple graphite, single layer graphite, or up to few layers. Graphite can be considered as the graphene. There are multiple parameters like kinetic conductance, quantum conductance. Those can define its conductivity, and based on those conductivity means kinetic conductance is one parameter that can define its electronic tunability. So this can exist up to with a significant value up to few layers of the graphite, up to 10 layers, means the thickness of one layer of graphite is up around, technically measured, this is 0.34 nanometer, up to 10 layer and more than that layer. Means if we increase the number of layers, only thing that we can attain means it's the reconfigurability will be reduced just because of reduced value of its kinetic conductance. Okay, so that is, this is the problem. Point is that like what is that graphite that we can understand, like graphite you can find in lead or pencil that we are utilizing since our childhood. Okay, and if you draw one line very means clearly, very crucially, and this is means of the order of thickness 0.34 nanometer, or in further multiple terms, then it can be called as graphene. So what will happen if you put some battery, then you can measure the current by applying some multimeter over here. You can perform this experiment in your laboratory or using your pencil and all other multimeter and simple things you can understand. Okay, and so here we had understood what is that graphene, what is electrical electronic tunability, and we are going to utilize DC biasing technique. So what is the significant, what are the repercussions that you had understood most thoroughly. And here this is a simple mathematical formulations that using which you can understand this, what is that graphene conductivity. This is can be defined using Cuber's formalism, using Roots model. And if Roots model is modified by for Roots model, you can study more about means this can provide us the view of conductivity, complex conductivity of any material at higher frequencies, complex conductivity. This is important point. uh, okay, means you can understand, you can study this in more detailed way. And here one thing that you can understand, biasing, if you are applying biasing on the graphene, then if this is a deposited graphene above this dielectric spacer, then this thickness of spacer is very important. This T is having very important role. And this applied DC required DC voltage to find out the particular value of chemical potential, representing chemical potential, which represents mu c is representing the chemical potential, and chemical potential is directly you can understand this is Fermi energy of graphene. Okay, so for particular to attain particular value of this mu c chemical potential of graphene, Fermi energy of graphene, we require particular value of voltage, and this depends upon the thickness of the substrate. If you apply larger thickness, then definitely you need means larger value of DC voltage, and in that case mu c will be smaller. You can understand. So this is a problem. Means for a larger thickness of dielectric spacer, you need larger value of DC voltage. And we had means calculated using some MATLAB parameter. Means in that way some relationship for different thickness of substrates, and in micrometers as well we had calculated the smaller amount of voltage required. You can further modify this relation as per your requirement. Okay, so one thing that we had understand, that we have to understand, this is like we have to select the smaller thickness of dielectric spacer, so that we require smaller value of DC voltage to find out the significant value of mu c. You can understand. So graphene works with the concept. This is the basic, or you can understand the basic physics behind the concept of theory of merging the graphene plasmons with the cavity resonance. That we have to first understand what is surface plasma. Most of the researchers have talked about this surface plasmons, and I hope you can understand what is that surface plasmon. You know the skin effect at the microwave. If you are the students of electromagnetics, then you know the skin effect. So what is that skin effect? Skin depth means this is a simple coaxial wire, simple copper wire. Suppose this is representing a copper wire. What happens if there is a current? If you connect one end of this copper wire with some current, some power supply, means there is a flow of current on this wire. So what will happen means current means electric field, you can understand. So what, where the electric field will be distributed over this wire, you can understand. It will penetrate up to few, means few micrometers, nanometers, few micrometers, and then beyond that it will be, this electric field will be completely zero, and that thickness is known as skin depth. I hope you are able to imagine this. So what is the point, like here there is Ohm's law of electromagnetics, J equals to sigma E. Okay, so if sigma is very high, so in that case E will be 0. E will be 0. Sigma is infinity, then J upon sigma, J upon infinity, E will be 0. So inside any conductor there will be no electric field. So simply this is a concept being followed by this wire, copper wire. Okay, this is a copper wire. So if we think about this copper wire, there is no electric field inside this copper wire, and up to few micrometers there is only existing field, and this is called skin depth. And this is the concept which led towards the development of this coaxial wire. Okay, so you can understand technically if this is a view of this, means this inside inner portion of this copper wire is useless to conduct the current. So we can remove this portion, and we can remove this up to the level of few skin depths, and we can just keep this up to the level of few skin depths over here. So it can carry the current, sufficient amount of the current, and then we can place another copper wire here. So it can another copper lead. So this can work as the coaxial wire. That coaxial wire we utilize in multiple applications, in televisions and multiple and telephonic lines, and everywhere you can understand. So this is the concept of skin depth, which has reduced the concept of this two wire transmission line. And what is that skin depth? You can further study this further investigate in that way, like what will be the means what will happen with this wave if we are working at the higher frequencies. You can understand this skin depth is reciprocal to the operating frequency. This the concept was being utilized at the microwave frequency and lower than that. Further, if we move towards the terahertz frequency, then what will happen? This skin depth will be further very much small, and most probably this all the wave will be confined on the surface only, and skin depth delta will be approximately zero and very small, up to the very few nanometer range, or at the means approximately few radius diameters of one atom. You can understand. So in that case, once you had you had started working at the terahertz frequency and you are going to utilize metallic boundaries, in that case all the wave is being confined on the surface, and that wave, if wave is being confined on the surface on a metal sheet, so this is the basic principle of electromagnetics. In the first attempt, if this metallic sheet is kept under the influence of some external electric field, electrostatic field, specifically static electric field, then there will be the first phenomena will be happening, like there will be the separation of charges, and that charges can be arranged in the form of dipole arrangement, or you can understand like this charge will be polarized, and that dipolar arrangement can provide us some electric field distribution in that way, and this is called surface plasma. So you can understand there is some incident electromagnetic wave, and once this energy is being soaked by this metallic sheet, so at metal layer interface there is a formation of dipolar arrangements, electronic dipoles, and then some field standing waves will be created over this dipole arrangement at metal layer interface. This will be called as this. This is being called as the surface plasmas. Another point is like if you further means if there is some standing wave, you can understand standing waves can have some resonance. Okay, if you just try to observe its resonance spectra, so standing waves, if there is some pre-existing standing wave somewhere in cavity interface or some in some any structures, so you can understand there will be the phenomena of resonance. So this surface plasmon will be providing some resonance respective to at the frequency respective to this dipolar arrangement. So we will discuss this in a further way. Okay, and this one wavelength is being called as lambda SPP, surface plasmon polariton wavelength. So what is that another word, polariton? Like any if there is an existence of surface waves, surface plasmons, and some electromagnetic wave interacts with this surface plasmonic waves, surface plasmons, then this combined composite effect will provide us some resonance, and that is known as surface plasmon polariton. Compositely, the combination of interaction of electromagnetic wave to the surface plasmons is known as surface plasmon polariton, and that can provide us some resonance, and that resonance can have the frequency of the order of lambda SPP, surface plasmon polariton wavelength. You can understand F equals to C upon lambda. And one more thing, you just see this is just the wave dipolar arrangement which is being generated at the metal layer interface. You just see if you put some, this is like surface waves at the in some river and water. Okay, you can understand if you put some external force, if you put some trigger point, some external field, anything in this generated dipole arrangement, so this can destroy this dipole arrangement. And once you are able to destroy this dipole arrangement, and suppose if you are able to destroy and you are again able to re-establish those dipole arrangements, so you can control those dipole arrangements in your own way. And if you are able to control those dipole arrangements, then definitely you can control the resonance too. So this is the concept, basic physics behind this theory that we had proposed, we had worked. So first we can understand graphene antenna. So what is that graphene antennas? Everyone knows about this. It's like we had understood, if we are going to utilize resonator of graphene material, simply this is working with some SPR arrangements, and this SPR arrangement will be providing some resonance. That's the point. So one thing that we had understood, like graphene can provide some means graphene can provide some tunable conductivity, and if we are designing the device using graphene element, then we can obtain the tunable electronic response over frequency. Likewise, this is reflection coefficient, tunable reflection coefficient using applied electrostatic bias. Second one, if we had applied this graphene resonator, and if we apply the trigger point, likewise we had discussed it over here. Here, if we put some trigger point somewhere, we are able to reconfigure this dipole arrangement. So here that concept we are utilized here. We had applied some DC voltage at multiple locations to trigger the dipole arrangement of this graphene and resonator, and here we are able to reconfigure this radiation pattern of this antenna. So we can obtain reconfigurable radiation pattern of this antenna. You can understand. You can go through this research work. One of my PhD scholar, Dr. Mohammad Farman Ali, he is currently associated with IIT Delhi as a senior project scientist, and he has worked on this tunable terahertz MIMO antennas, and he has utilized the graphene resonator to develop the MIMO antennas, and he had worked on this similar concept. So only we have to understand here, like limitations. What are the limitations of graphene antennas? These are not efficient. This is the most prominent or significant limitation or restrictions imposed on this graphene resonator. What is happening like graphene? If we think about graphite, so you can understand there are a lot of studies. This has been reported in the literature. The absorption coefficient rate in specifically in lower terahertz frequency ranges, absorption rate of graphite in lower terahertz range is very high, and this can provide us very small means very small radiation rate, scattering rate. So since we can understand graphene is an element of this graphite, so graphene can provide us very high absorption. So most probably this is not suitable for designing efficient antennas. While terahertz frequencies and terahertz applications are already absorptive, this high frequency is attenuative in nature for wireless propagation link. So in that case, these frequencies, these antennas may not be suitable for terahertz frequencies. These can hardly provide the efficiency up to 20%, 25%, and less than that too. Our gains are very smaller. In fact, if we discuss about graphene antennas, they can be suitable in receiving applications like loop antenna and direction finding applications. These are very less efficient antennas. So in such, in fact, EMI sensing applications. But for transmission purpose, graphene antennas are not that much suitable that we are thinking over. Only these are suitable for reconfigurability. But if our purpose is not fulfilled for the transmission wireless communication, then in that case these graphene antennas cannot be of our use. So ultimately, if we rethink over metallic antennas or dielectric antennas, these cannot provide electronically reconfigurable response. If we think about graphene antennas, they are not efficient, they cannot be utilized in wireless applications. We have to go for further category in that case. So this concept that we had proposed, the merging the graphene plasmons to the EM resonance to micro nanoscale cavity, that can help us a lot in the near future. So here we had worked on the hybrid antennas or hybrid resonator. This will be most means it will be fabulous to think means call it like hybrid resonator rather hybrid antennas, because we are going to design antennas, absorbers, and other devices using hybrid resonators. So what we do in case of hybrid resonators, here we utilize a dielectric material, dielectric resonator, and we coat some graphene element over it. And in the similar way, so what happens with this hybrid resonator, we are able to obtain the characteristic of resonance of dielectric resonator. And if we coat this graphene element and if we apply some variable DC voltage supply over the graphene, we can tune the resonance of this dielectric resonator. How this is able to tune the response, graphene is able to tune. Means point is like graphene is not providing its a resonance, it's a radiation. Only dielectric resonator is providing its a radiation, and graphene is providing electronic reconfigurability. So in that way, already you know this dielectric antennas are highly efficient, metallic antennas efficient in comparison to graphene antennas. So in that case, at higher frequencies, we can utilize metallic or dielectric antennas, and we can incorporate graphene material in that. And on that basis, we can propose some hybrid resonators, and we can obtain high gain efficiency in case of antennas, as well as we can obtain electronic reconfigurability. So this is the basic concept, basic mathematical concept that we had demonstrated specifically for the resonator. Right now we had reported in the literature for the case if metallic resonator is working with the fundamental mode. We had continued working on this concept whenever this resonator, metallic resonator or dielectric resonator, is working on higher order modes too. And recently one of my PhD scholar had finished his PhD on this concept of higher order modes and this concept of merging the graphene surface plasmon resonance, and soon we will be able to report it in some literature as well. Okay, so here in the case of metallic resonator, so what is the concept you try to understand is, here we had taken this cavity metallic resonator, ring resonator most probably, and this is of the dimension of lambda by 2 if this is working at the fundamental mode. and so resonance will be, you can understand, this can be obtained at the respective frequency to the lambda by 2. Second one, we had incorporated the graphene element in this whole resonator. We had perturbed this whole geometry. We had incorporated the graphene element, and size of this graphene element, already we have discussed this. We are working at the terahertz frequency, and everything now is being considered in form of this lambda SPP that we have discussed. This lambda SPP. Here dipolar arrangement remains of the order of lambda SPP. So one thing that we can understand, this dipolar length of lambda SPP can provide us resonance at the same frequency whatever is being provided by this cavity, metallic cavity, but size of this dipolar arrangement is much lower, and this is the well-known fact of this graphene literature. This can provide us some miniaturized dimensions. Okay, so if these are miniaturized dimensions of graphene element, and here so point is like this graphene element can provide resonance at the same frequency, resonance at the same frequency whichever is being provided by this metallic resonator, but with some smallest size. And here we had taken this the diameter of this graphene element of the order of lambda SPP. And here we can understand there are multiple mode index of graphene can be obtained. Graphene surface plasmons, those can be obtained mode index 1, mode index 2, mode index 3. This is a study which has been reported by this means literature. And furthermore, we had calculated the dimension length or resonant frequency of this lambda SPP of graphene element using Fresnel's dispersion relation. Okay, Fresnel's dispersion relation. So here, whatever we are taking using this Fresnel dispersion relation, we had applied some electrostatic bounds, and we had calculated the surface plasmon polarized wave vector. And based on this wave vector, this can be modified in case of graphene using Roots Cubo's formalism, and then based on that wave vector, we can calculate lambda SP. Once we are able to calculate lambda SP, we can calculate F resonant frequency FSP. And once we are able to calculate FSP, we can match this FSP to F resonant frequency of cavity, metallic cavity, and we can obtain the same resonance frequency with multiple dimensions. So in that way, we can make a hybrid of metal or dielectric resonator to the graphene element. And one of my PhD scholar, he's going to defend his PhD thesis. Dr. Durgesh Kumar, means Mr. Durgesh Kumar. Right now, he has submitted his thesis on this investigation on the interaction of graphene plasmon to the terahertz devices, and he has reported this concept in his thesis, and we had published multiple papers in this domain. And what is that concept? We had designed one antenna containing this hybrid resonator of metal and graphene. Okay, so antenna without graphene, antenna with graphene. Okay, so you can understand antenna without graphene, black color, antenna with graphene, blue color, and with graphene with the chemical potential 0.0 electron volt, and with the chemical potential of graphene 0.3 electron volt, there are two bands. Means there is one resonance just from graphene and another resonance just from metal. You can understand. Means we are able to separate those resonances for a particular value of chemical and a chemical potential of graphene. You can understand that way. And furthermore, that has been studied well in further way. So there is a fringing field or just being generated by metallic cavity, and if we apply graphene over here, we incorporate graphene in this antenna, then some SPR with mode index 1 will be existing along with the graphene fringing field, and both will be providing resonance together in form of multiple bands, multiple resonances. And that mode index can be changed. Mode index of graphene can be changed to 3, 2, depending upon the Fermi energy of the graphene. And then in that case, we can obtain the multiple resonances in the antenna response. You can understand. And this is further visualization of this fringing field and for the mode index, SP wave mode index. Here we are not having facility to fabricate it right now at the terahertz frequency. In fact, if we are able to fabricate, we cannot characterize, we cannot measure the antenna response. We are not having those facilities. So we had means right now all the researchers around the globe are working in that way. They are validating their response using multiple theories. And this electrical circuit model, theory of multiple reflections, depending upon the geometry or required device, there are multiple ways which are being utilized to validate the response. In case of antennas, ECM is fabulous method. So this is being utilized. One thing right now we can understand, like in this case, in this antenna structure, you can understand there is a broader surface area of interface of graphene and metal. That surface area plays important and a vital role. And how this is impacting the antenna response, a broader surface area which is being covered by graphene will provide us lesser efficiency, will reduce its efficiency in the operating when the plot at the significant level. This is just think, this is radiation efficiency without graphene, this is radiation efficiency with graphene, 30%, 20% of the operating. This is the most scary thing that we had utilized with this theory. So we had further modified this theory, we had incorporated the perturbations. Okay, so we had incorporated the perturbation in the graphene antenna. Means, so what we had done, we had reduced the surface area of the graphene. Okay, and then we had obtained this radiation efficiency. This using this similar concept that there is a merging of the metallic resonance and graphene resonance, that we had concept that we had utilized. Now somehow we were able to preserve this radiation efficiency. This radiation efficiency, this red color, this full graphene loop, if we fully cover this loop portion by graphene, then radiation efficiency is, you can, this is fluctuating. And if we reduce the surface area of graphene, then radiation efficiency is significantly improved, but this is not up to that mark still. And one thing that you can understand, this is the field distribution on the graphene, with fully covered with the graphene area, then surface plasmons or field distribution confinement will be looking like this. And if we reduce the surface area, then field confinement will be looking like this. Okay, and that will help reduction in this graphene surface area to the metal interface will help us in improving the efficiency. So that concept has been further modified, and what we had recently proposed here, we had utilized a loop of graphene in place of full graphene patch. So this had significantly worked with this our concept and this means total hypothesis. So you can understand this is the antenna gain without graphene 6 dBi, 5.4 dBi, and this is gain 5.73 dBi with graphene, 6.79 dBi with graphene. So this is significant improvement, and in fact we can retain the antenna far field parameters with the uses of graphene. Still there is a problem, like you can understand we had further modified this concept to walk over this graphene. We had recently, what we had done, like we had perturbed this metallic resonator, and this perturbed area has been filled with the graphene only. Rather we had utilized full metallic resonator. We had perturbed this resonator before employing the graphene over here, and this had provided us the significant most fabulous results. This is the response without graphene, this is response with graphene. So bandwidth has been little bit enhanced, radiation pattern is significantly preserved, efficiency and gain are significantly preserved. You can understand this is efficiency. Antenna 4 is without graphene, antenna 5 is with graphene. So gain approximately similar with and without graphene, efficiency is approximately similar with and without graphene, only bandwidth has been enhanced. And one more thing, that applying the chemical means variable DC supply, we can tune its radiation pattern. You can understand we are able to tune the radiation pattern. Okay, and here this tunability in radiation pattern can further be investigated and explored in that way. Here for particular different value of chemical potential, this scattering parameter, and then this tunable radiation pattern in multiple directions, one lobe, two lobe, narrow spread, broader spread, you can understand. And what is happening on the graphene, we can study this in further way. This graphene, this is the graphene area, and without graphene or with the graphene with lower value of chemical potential, there is no generated SPR, you can understand. But once we increase the value of chemical potential of graphene, the SPR will be generated, and that's those SPR, a lambda SPP can be tuned based on the applied DC voltage. And here you can see lambda SPP has been tuned. And once you are able to tune this lambda SPP or this arrangement of this graphene surface plasmon, you will be able to tune its radiation pattern or frequency. You can understand. We had calculated this lambda SPP using similar mathematics that we had employed using Fresnel's dispersion relation and incorporated in this Cubo's harmonics. We had implemented a MIMO antenna with this concept as well, and this is fabulously working. Theoretically, we had reported this in this. This has been accepted in IEEE transactions on plasma science recently, and this concept has been further utilized to design absorber as well. So what we had done, this is a metallic absorber providing two resonances, and a graphene has been engraved beneath to this metallic ring resonator, and now we are able to obtain three resonances, and this third resonance can be tuned over frequency using applied DC voltage. So you can understand it can be merged to two resonances and can be separated, and this is beautiful thing that you can observe over here. Using the similar concept, you are able to obtain this tunable. So here up till now we had discussed about this cavity resonator of metal and hybridized with the graphene element. The similar concept we had utilized long back in the dielectric resonator and graphene we had utilized the hybrid resonator of dielectric and graphene. This is this absorber without graphene, absorber with graphene, response with and without graphene. Without graphene, there is no confined field in the dielectric absorber, means there is small amount of confined field. But with graphene, there is a highly confined field. And if we change, and this is the field distribution on the graphene, this is the surface plasmons being generated in the case of without graphene with graphene. Once we will tune this surface plasmon using externally applied DC supply, we'll be able to tune its response. So this has been, this was published in IEEE transaction in nanovirus science. This was the first concept I had reported long back. This tunable terrace dielectric resonator antennas. I had utilized this means dielectric resonator hybridized with the graphene, and then I observed this tunable response over frequency. And this research work has become the basis for multiple studies being reported right now globally. And furthermore, this concept has been evolved to obtain this biconical radiation as well, with the hybridized of this means as well as this tunable CP response as well, hybridization. Ultimately, we had granted this technology, we had patented in and published papers in multiple journals. Right now, we are on the way to validate this experimentally with the help of some collaborations with some means, professors who are working in rich laboratories like IIT Kharagpur. Professor S.K. Vashne is working there, and we are working in collaborations. So this is there are further things. This is our research team. There are many more members which are not available in this photograph, and who are working day and night to means to do something in this domain, in the case in the domain of terahertz functional devices. And if there is any query, please let me know.
Dear participants, if you have any query, you can drop in the chat box or raise your hands. Sir, I have one query. May I ask, sir?
Yeah, please.
Sir, in slide number 54, where we are calculating the field enhancement
Yes, this
with
one.
respect to length of the patch, sir.
Yeah.
So, for this, sir, how we have to do the length of the patch in the negative, it is also mentioned, the range of the x-axis.
No, this is just a representation on a number line. That's it.
Okay, so sir, how should I calculate the field enhancement now?
Let me tell you. Like we had imagined this antenna origin at the center of this antenna structure. That's it. So this is negative range, negative number line only. Okay, I hope you had understood this. I hope you had understood the concept of negative number line. Is there any
Yes.
problem?
No problem, sir. But in the formula, I have to put the things and find out the graph, no?
Means we can consider the positive side only for putting it in the formulations. Okay, or like means whatever we had designed this antenna structure in CST simulator, we had
Yes.
imagined the origin at the center of this antenna structure, and the similar thing we had reported over here. We can keep origin somewhere else to report it in a positive way only.
Mm-hmm.
Okay, we can keep origin here. So this is origin at the center, and if origin at the center of antenna structure, and we are either side we are means calculating the field, and field enhancement can be calculated means using, you can apply some electric probe in the nearby region of this antenna. There is an option available in CST simulator as well, and in case of means maybe in other simulator as well, you can apply some electric probe here above
Mm-hmm.
some height in far field region maybe, or near field region. This is basically near field. So in near field region you can apply some electric field at multiple heights, and you can calculate electric field without and with gripping. So that will provide you directly the field enhancement factor. That's it.
Okay, sir.
Hmm.
Thank you very much, sir.
Yeah. Any other question? If there
Hello,
is any other question.
Sir,
hello.
one question is there from the participant.
Yeah, please.
How to give electric voltage, VG?
How to apply electric voltage somewhere? Okay.
Yes, sir.
Hemant, Hemant is asking about this, please.
Okay,
Yeah,
Hemant, we will unmute you. Give a minute.
yeah, Hemant, there is an option like simply what we are doing is in case of simulations like in CST you can, there is an option to change the chemical potential. Okay, but if you are going to utilize other simulators like COMSOL multiphysics and other HFSS or any other simulator, so there is a way. Let me tell you what is that way. I had started working in that domain, and so what is that? Like this is, I had calculated the using this this formulation of graphene's conductivity. I had means calculated using MATLAB. I had plotted this whole by putting the value of every parameter. I had plotted this in MATLAB. Okay, so for a particular value of chemical potential, here first I had calculated this relationship BBI and mu c, relationship between BBI and mu c. So correspondingly, suppose up to 10 volt, I need something chemical potential zero point 0.8. So for zero point 0.8 value of chemical potential, I require 10 volt. So this is one thing. 10 volt battery, application of battery equivalent to 10 volt will be providing in real life, will be providing chemical potential uh, around zero point 0.8 electron volt, while thickness is kept in that way. Okay, in that you can understand, and you can, in that way you can further calculate for multiple thickness too. So this is first point that we can understand. we had established the relationship between chemical potential and this DC voltage. This is hypothesis, hypothetically observed value, and we had simply applied this chemical potential here in graphene's conductivity, and I had obtained the value of graphene's conductivity using MATLAB, and that further values, those values I had extracted corresponding to this sigma g using Rhodes model. I had means there is a norm, means there is a formulation available. This can provide us the relationship between complex permittivity and complex conductivity. So I had obtained the relation means data values for complex permittivities. So once I will be able to get those data values for complex permittivity, I can just take means from MATLAB I just can take extract it in form of .csv format or in multiple formats, that whichever is being allowed by your full wave simulator. I had imported that file in HFSS or some other simulator, and then I had worked with that in that way. Okay, so there is no direct option available to apply some DC battery and that in any simulator. We can correspondingly calculate the conductivity or permittivity corresponding to particular value of voltage, and we are means researchers around the globe are working in that way. I hope you had understood.
Okay. Thank you, sir. I am Hemant Kumar Vasa, NIT Delhi. Sir, actually, I am one new in terahertz. Sir, I have tried, but I am only working in CST only allow for chemical changing by changing the voltage. Sir, what is the change of chemical voltage range of UC? That means chemical
Generally,
potential.
okay, you just want to know the range of chemical potential that can
Yes,
be
sir.
obtained. So you can understand,
Yes.
like usually in practice means researchers are means experimentally that has been reported is up to 1 electron volt, 0 to 1 electron volt. Point is that you can understand, like this is the case here. The thickness of substrate is in nanometer. In actual micrometer devices, you are taking the thickness of substrate in micrometer. However, you can utilize some polysilicon thin film to just reduce the thickness. Okay, so what happens, you you cannot go beyond the DC voltage. There is a restriction of application of DC voltage supply. Like DC voltage cannot be beyond means up to 25 DC volt, means DC, the 25 voltage of DC battery is very high, and beyond that is we require very high source. You can understand. Okay, likewise we cannot go up to 240 volt and 450 volt, 440 volts in likewise AC. There is a huge variation. In DC voltage we are having low range of means voltage supply that we can apply. So accordingly we can select the thickness of substrate, and we can select the value of chemical potential, and we can select the value of chemical potential experimentally up to the range which can be validated with the applied small amount of DC, which can require a small amount of DC voltage supply. I hope you can understand. And 1 electron volt is means experimentally obtained. Researchers are reporting beyond that to in theoretical studies, but I had hardly seen means experimentally researchers are working beyond 1 electron.
Okay, sir. Suppose I want to design any reconfigurable band notch antenna.
Okay.
Terahertz.
Hmm.
Then what is the process, sir?
Process, like one thing that I had my process is simple. I had reported one thing. I'm utilizing hybrid resonator. Okay, I think I had this one. There is one thing. I had reported this reconfigurable terahertz antenna with reconfigurable band notch characteristic. I had utilized hybrid resonator, metallic resonator plus graphene strips. Okay, and the location of graphene strips can be defined based on the nulls of electric field being created on the antenna dipolar means resonator. So once you apply this graphene strip, you will find band notch characteristic and you can reconfigure. This is one thing that you can follow, and there are multiple ways. Very first thing that you can follow, this is monopole kind of structure, and then you can modify in multiple. So we had recently reported multiple papers, research papers on this filtering characteristic of band notch characteristics being engraved with reconfigurability in terahertz antennas, providing wideband applications, wideband response. Yeah.
Okay. Thank you so much.
Yeah, thank you. Okay, Hemant.
Hello.
And another question from I think
Yes, sir.
Swati sir: how much relaxation time would be time we should consider for designing graphene as material in any software like system? Okay, this is very good question, Swati. Like tau is the relaxation time that we can understand. So here means what is that tau? We have to understand what is that tau. Tau is relaxation time, and what is relaxation time? This is reciprocal to scattering rate 1 upon gamma. Okay, so scattering rate and tau, what is that? First we have to understand that scattering relaxation time that we can understand from our 12th standard physics means if any there is any free particle, this is this starts moving, interacts with another particle, means there is a first collision, and then it changes its path, comes to another way, and then again interacts to another particle, and then its path is again changed and interacts with another particle, and then its path is changed and then interacts with another one. This is a way of moving any free charge. So we take the two consecutive interactions, two consecutive collisions, and this is the time between two consecutive collisions. This is called relaxation time. And if we calculate the average time of between two successive collisions, then we can calculate the mean relaxation time. Ultimately, suppose why just think about why this collision is occurring. This is very important point. There may be some point. One, fabrication issue. Suppose you had fabricated graphene and its surface is not perfectly smooth. This is having multiple grooves. This is hazard surface. This will provide roughness. This roughness factor is very high. So it means we can think about quality of graphene. This quality of graphene fabrication is poor, or you can call it quality factor of graphene is poor. In simple language that we can understand, quality factor of graphene fabrication is poor. So what will happen? Electron free charge will come up. This will unwantedly interact with multiple surfaces, and if there is perfectly smooth surface, there is no roughness, then electron of free charge particle can move up to a long distance without any collision. So with this means if quality of fabrication of graphene is high, there is no collision. If quality of fabrication is poor, there is high collision chance. So if in case there is no collision of charged particle, in that case there will be no relaxation time. How much will be relaxation time? You can understand infinite, very large relaxation time. This means time between two successive collisions will be infinite ideally, or there will be no collision. That's it. Infinite means there is no collision, means our fabrication is very that much perfect. There is no means roughness, roughness, and charged particle may follow the ballistic transportation. Technically, we call it ballistic transportation. If charged particle is moving throughout the surface on its path without any collision, then this is called ballistic transportation. If any charged particle is following ballistic transportation, then there will be high value of means large value of relaxation time or high value of quality. So large value of quality means relaxation time means high quality of fabrication, that is very rare of means rare to achieve in case of nanoscale or 2D sub fabrications, 2D material fabrications. So ultimately we have to reach towards this most practical value. Lower value of relaxation time means poor fabrication of that can be done in real life. Means so somehow there is a chance means from 0 to 1 picosecond we can select in case of graphene this relaxation time value. So somehow we can take it in some mid zero point 0.5 picosecond and towards the lower value to represent the poor fabrication quality of graphene. And if we are confident enough, like we will be fabricating graphene with very much high quality, in that case we can take this value as much high as possible to facilitate the ballistic transportation. I hope you had understood this physics.
Yes, sir.
Any
Thank you.
other question, please?
Hello, good morning, sir.
Yeah,
Sir, I'm Vikram Maurya from MNIT Jaipur.
yeah, Bikram.
Sir, my question is related to MIRT theory and shielding effectiveness calculation.
Yes, yes, Vikram. Since long back, I remember that you had dropped an email to me. I was busy in my means everyone is having personal life. I was busy
Yes,
in
sir.
my family life, so unfortunately, I couldn't reply you in that way. I tried to find some time, but I couldn't because of I have expansion in my family. You can understand. Still,
Yes,
I
sir.
am
Sure,
going
no
through in
issue.
that way. So I'm sorry for that. I couldn't reply you means in that positive way. But I would love to tell you about this MIRT. MIRT is a way to understand the basic phenomena means of basic operation physics of any absorber or not only absorber any multi-layered structure. Okay,
Yes, sir.
so there can be one specific lecture it requires means explaining MIRT would be requiring approximately 2 to 3 hours lecture to particularly explain how this physics is working, multi-layer physics is working. Like let me tell you one thing for your clue to understand. Like
Sure.
suppose uh, okay, suppose there is a case. Okay, there is one layer of graphene, another layer of dielectric, and then another layer of another dielectric. So graphene's permittivity is different. Okay, here you can see the permittivity of this graphene material is different. Permittivity or dispersive characteristics. Better to call it dispersive characteristics of graphene is different. Dispersive characteristics of this dielectric resonator is different. This is made up of silicon material, and dispersive characteristic of this lower substrate, this is of silicon dioxide, this is different, and then at the bottom there is a metallic ground. So every layer is having different dispersive characteristics, so this is called multi-layer structure. So what happens, suppose you just impinge some electromagnetic wave on at somewhere at the top surface, then what will happen? At suppose there are multiple layers arranged in that way, layer 1, layer 2, layer 3, and multiple interfaces. Now you had arranged layer 1, layer 2, layer 3, layer 4. Okay, now there are in multiple interfaces which are being created: interface 1, interface 2, interface 3, interface 4, and interface 5. Suppose you put some electromagnetic wave over here. Okay,
Yes, sir.
and then what will happen? One one portion of this wave will be means transmitted, reflected, another portion will be reflected. Now again at this interface one portion will be transmitted, another portion will be further reflected back, and every wave will be following the similar principle, and there will be, you can understand, multiple waves will be existing at multiple interfaces. Large number of interfaces include large number of reflections, and you can understand if large number of reflections are going through a single geometry. Suppose there is a bounded geometry within certain boundary conditions existing within certain restricted within certain dimensions, so in that case you can understand this can work as a cavity, and then multiple reflection and refractions can create multiple existing waves and you can understand interference will be existing together. This is the basic intermediate physics that you can understand. Existence of multiple waves with different phases can provide us the destructive interference, and if waves are with the same phase, then they can provide us some constructive interference. Okay, so in case of antenna we need to enhance the gain, so we need constructive interface. In case of absorber kind of device, we need to disperse the wave, we need to just, means you can understand, we need to sink the wave. So in that case we have to find out the destructive interference. So this is one thing, this one thing that we had, we can allocate one numerical parameter for each wave, reflected wave and transmitted wave. Now there is one medium 1, there is medium 2, and in further there are multiple mediums if this is a multiple layer structure. Okay, this will be very complex to understand if number of layers are large. If you want to understand the theory of multiple reflection, I suggest you to work with two mediums only, medium 1 and medium 2, and containing single interface. So single interface will provide you one incident wave, one transmitted wave, and one reflected wave. Once you are able to understand the concept of single interface, then you will be able to crack the concept of this multi-layer interface. And now once you will understand this physics, one more thing I would like to tell you, there is geometric progression. Once, if you want to, like suppose there are two waves right now, okay,
Yes,
and
sir.
here suppose you had applied reflector. In case of absorber, this reflector, there is dielectric spacer, and this is resonator. Incident wave in medium 1, reflected, reflected, refracted, reflected, and then from reflected it will be reflected, again this will be reflected, and then following the further course. So there will be large number of waves in one interface medium. Okay, so in that case these waves can be calculated using geometric progression. I would send you some one research paper which can provide you the way how to calculate this whole composite wave in medium 1 and medium 2 using geometric progression GP. And I'm preparing one document which can help us, means help the researchers to understand this means CST, means employing this theory in CST microwave studio is another topic to understand. This will take a lot of time. Okay, this ultimately requires more than 1 hour to understand if somebody explains. So point is, like, I'm preparing one document, I'm writing a book right now, and I'm trying to report that concept, how to means how to correlate the this mathematical theory of this MI theory of multiple reflections to this full wave simulator, any full wave simulator like CST or any HFSS or console or any other thing. So that draft I can provide you for your study once it is completed soon. Okay. In fact, I assure you, I'll provide it you before the publication of book. Okay.
Okay, sir.
Okay,
Sir,
Vikram.
only one doubt is there, sir.
Yeah.
If there is a multi-layer, then we have to select our port at every layer.
No. There is some other study. We can select. We can go for means we can go for this process as well, but there will be difficulty.
Okay, sir.
Okay,
Sir,
there will be a difficulty.
and sir, in case of shielding effectiveness calculation,
Yeah,
whether we have to choose the coupled mode theory or decoupled mode theory.
decoupled mode theory. For
Decoupled.
for calculating the shielding effectiveness, we have to select the decoupled mode theory, because you just try to understand the basic concept. This, if we are working with the absorber, this
Yes, sir. There is a
this reflector is simply a reflector, metallic geometry.
yes, sir.
Simply remove this metallic geometry. Now you have to calculate the effective index of this rest of this structure.
Okay.
Okay, I hope
Okay.
dispersive property, dielectric property, or other resonator, including resonator, whether this is of any material. only you have to remove this ground plane, then
Yes.
calculate the effective index and then go ahead.
Yes, sir. Okay, sir. I got.
Mhm.
Thank you, sir.
Okay, Vikram. Any other question from participants, please?
Sir, I think no more questions are there.
Okay.
Participants, you can ask if you have any query. Sir, I will also try the field enhancement and try to apply in the CST. If I find any problem, may I mail you, sir?
Sure. Anytime I'm available. Okay. I'll discuss. We can connect online as well. Okay.
Yes.
A lot of platforms available right now. Okay. So there is one thing I would like to share with the participants. We are having some about opportunities. You can go through my website. This is gauravvaishnav.com, www.gauravvaishnav.com, and we are having means uh, this one. Uh, we are having one fellowship for UG students. If for UG students from other institute other than NIT Patna, on the name of my father. Okay. Means we will provide you expenses of means expenditure for stay during summer internship for at least for one candidate from my own means you can understand, and you can fill out this form at this link at the career opportunity available on my website. And here this is my team. These are my team members. Okay, you can if you want to discuss anything, you can also connect with those research scholars. Means many of them had finished their PhD and few of them are carrying means continuing, so you can connect with them. They are they are currently employing in multiple good laboratories in different IITs in other institutions in foreign universities too. They can help you in any way. If they can help you, you can connect with them too. And if you just want to drop some query, and you can think over it. And one more thing I would like to share. There is one special issue. Right now, I'm the editor of that special issue. You can submit your research papers to this journal, Discover Sensor. This is open access journal, means being published by Springer and Discover Physics. Right now, this Discover Sensor is free for publication till December 25, and you can submit your manuscript to this by considering this special issue terahertz. You just log into this journal website for submission of manuscript, and just submit your manuscript by opting this terahertz functional devices for 6G systems, and submit your manuscript related to any terahertz or any other antenna or anything you can just want to submit. And means I would support you in this in this journal Discover Sensor. Discover Physics is also means propagating this issue, but this is means taking some charges. I'm the guest editor for this, and also you can submit your research paper to this conference if you want to visit Aligarh. Uttar Pradesh is right now very popular state, and if you want to visit in our area, Aligarh, then this is Impact Conference. Impact 2026 is going on, and we are also conducting one special session there, terahertz functional devices for 6G system. And you can submit your research papers to this journal as well, wireless personal communications. So this journal is also accepting manuscripts on different terahertz functional devices right now, and I would like to expect your manuscript in these 3 points, three functions. You can understand some other facilities you can go through on our website. Thank you for listening me, and I think if you have any query, just drop an email to me. That's it. Goodbye.
Thank you.
Okay,
Thank you
Swati.
very much, sir. Thank you very much on behalf of EICT Academy and Electronics Department, MNIT Jaipur. Thank you very much, sir, for accepting the invitation. And the session was very much helpful, sir, for the antenna as well as for the absorber students.
Yeah,
Thank you very much.
thank you, Swati. Thank you, Vikram, and everyone. Thanks for joining.
Thank
Thank
you.
you. Dear participants, next session is from 11 a.m. You are requested to kindly stay connected.